All right, high school physics, we are back. And the last time we did a video, we talked about what to do with forces at an angle. And here's what we have to deal with now. What about inclines or ramps? Okay, so just kind of a quick review about our normal problems to kind of think about free body diagram. I'm going to, excuse me, draw directly on our figure here and think of all the forces. If there's no incline like this first example here, you've got the force of gravity of your object acting downward, right? You've got a normal force of the surface pushing back on the box, right? I'm going to actually redo this because I want to make it a little bit more proportional, right? Our force of gravity is straight down, and the box here, the normal force should be roughly equal. You've got this applied force to the right here, and then if the box is on a surface that has some friction, you have friction going the other way. But the question really becomes, what do we do if we have a ramp or an incline? Okay, so this is really what we're going to talk about today is what do we do about that? And I'm going to show a little bit of this in class with you, but I want you to kind of see that when we tilt and have this incline, notice here that I've got a surface right here, this dotted line, right? And it has an angle to it. That is our theta angle. The amount of incline or tilt to that angle is definitely going to kind of affect our problem. And so we're basically going to have to kind of figure out what to do with it. So if I were to think about what forces are acting on this box now, well, we do have a force of gravity straight down, right? Because force of gravity is always straight down. When we put our normal force on here, remember the normal force is always perpendicular to the surface. So our normal force is more kind of along this direction here, 90 degrees to the surface. So our normal force and our force of gravity really are no longer in line with each other. And that's going to be a problem. And then we think about our applied force up the ramp, and then our friction, which acts along kind of the surface here between the box and the ramp itself, kind of runs that way also. And so if I were to really draw a free body diagram out here to the right, this might make this a little bit more clear, is that we've got a force of gravity that's straight down. And then we have kind of this incline here. Probably exaggerated my angle a little bit, but I think you'll kind of see what's going on. And then my normal force, remember, is perpendicular to the surface itself. And then up the surface, that's really where our applied force is. And then down the other direction is our force of friction. Here's the problem we face is if you look at this, the forces are not all in the X and Y plane. And so what we have to do to be able to do these problems, we kind of need to redefine the X and Y axis. It's no longer going to be a straight up and straight down scenario here. Since 3 of my forces out of 4 seem to kind of somewhat line up, see how this and this kind of line up together. We've got 3 out of 4 of them that are within 90 degrees kind of each other. Here's what we're going to do. We're going to think of it as like tilting your head. We're going to define this line along where the applied force and the force of friction is. We're going to say that's actually our X plane now. And then up and down where that normal force is, that's going to be our new Y axis. So there's really only one force that doesn't line up in the X and Y plane. Okay. Now, one of the hardest parts of this process for you to catch is the amount of tilt, which I'm going to draw this line here. That's what the normal horizontal would be. This theta angle right here, the amount that angle is tilted, or our angle of incline, is exactly the same angle as between our new y-axis and our straight down line of the force of gravity. So the amount that this tilts is equal to the amount that is tilted in terms of our new y-axis. That is probably the biggest and hardest concept to catch in this process. Okay, if you think about, we have a small angle. Let's say this theta angle right here was very small. then this theta angle tilt would be very small. If this theta angle here is much bigger, then it's going to tilt that theta angle much bigger also. That is probably the most important thing to catch, is that the angle of incline is equal to the angle of tilt for force of gravity. Okay, so what we're gonna do here, you can probably kind of see where this is going. We're gonna have to redefine this x and y axis, and then we're gonna have to deal with, there is a trig triangle. I'm gonna use orange right here. There is a trig triangle that shows up right here, a right angle. And if you think about it, there's the theta angle in the middle here. There's a y component, and then there's an x component of the force of gravity. So we're going to use trig as we solve these problems, and it's going to all go back to making sure that we know what the angle of incline is here in our tilt. Okay, and I'll help visualize this a little bit more in class. At this point, I would just say make sure you kind of catch that these two angles are going to be the same as we move forward and do some problems. Okay. All right, let me clear our screen. So kind of moving on, here's kind of another example here of that tilt. And if you think about it, if I were to draw directly on this diagram right here, let's call the center of our box. If we were to go straight down from that force of gravity, right? Then there is the normal force straight up right here, right? And what I'm trying to help you catch is that if we redefine this plane right here as our x-axis, and we redefine this right here as our y-axis, then this angle, theta, is equal to this angle here, theta. And then what we're going to do is we're going to use trig to find the parts of the force of gravity. Okay, notice here this angle of incline was actually bigger, it's steeper, and therefore this angle inside that triangle is also bigger. Okay, we'll have to use trig to kind of solve things, but that's where we're headed. All right, let me do a couple of sample problems with you. So here's our first sample problem. It says we've got a box that's being pulled up an inclined plane at a constant speed. That's important, right? Constant speed. Not sure why they got selected. Let's unselect that. Okay, try that again. A box is pulled up an inclined plane at a constant speed. That's important. The angle of the incline, so this little angle right here is 25.0 degrees. And the applied force we know up here is 25 newtons. And we're told that the mass of this box is 2.50 kilograms. Okay. The first thing we're going to do is we're going to draw a free body diagram. And I'm going to kind of do some of the parts of the problem to the left, to the right. So I'm going to try to get it all on this page right here. So what I'm going to do, I think I'm going to start right here with our free body diagram. Okay. Think about what's going on. We've got a box. And straight down always is our force of gravity, right? So we have that force. Other forces acting on the box. Well, we have a normal force, but remember, because this is at an angle, in fact, I'll go ahead and kind of put a dotted line in our diagram. And that's sometimes the easiest thing to do, is to get yourself a reference. Then 90 degrees with that is our normal force, okay? And then up the incline, so this force applied right here up the incline, I'm going to call FA. And then the other direction, so down the ramp, that's our force of friction. So we have four forces acting on this box. Okay. Now, there are times where we'll say, go ahead and draw kind of a dashed line to represent the sort of the components of the force of gravity. So here's what I'm going to do. I'm going to go ahead and do that straight down from FN. I'm going to draw some red dots, and then parallel to the force of gravity and the applied force, I'm going to draw. And that just gives you kind of an idea of that right there is our triangle that we're dealing with. okay? So because we're going to have to use little trig to kind of break things into components. The second part of this problem, it says, is to go ahead and find Fg. Remember, Fg is just mg. So to find the force of gravity, we're going to take the mass, which is 2.50 times 9.80, and we plug that into a calculator. 2.50 times 9.80, and you get 24.5 newtons. Okay, so that would be the straight down force of gravity. Now, here is sort of the new part, is that we're going to find the x and y components of the force of gravity. So I'm going to go back and kind of redraw. We've got a force of gravity downward. Okay, we're going to kind of redraw this as a trig triangle. And what we're trying to find is we want to find FGY. So we want to find this Y component. And then we want to find FGX, this X component over here. So we're finding the other two sides of the triangle. And then just remember, there's theta, that's our angle. Okay. Now, this is a little bit different than what we did with forces at an angle. And here's why. Because if you think about which force is opposite of the angle, is your FGX, okay? So to find FGX, remember the opposite side is going to be the sine ratio. So sine of theta is going to be, in this case, FGX over FG. So if I do cross multiplication here, it's really these two multiplied together to equal FGX. So force of gravity X is going to be Fg, which I just calculated that down below to the left, 24.5 times the sine of, and then we have an angle of 25.0 degrees. So I'm going to punch that into a calculator. So if I take, first thing I'm going to do is hit my sine button, 25, close my parentheses, multiply it by 24.5, and I get a number of 10 point, I'm going to round this, 10.4 newtons, 3 sig figs, okay? And then we're going to do the exact same thing for FGY. FGY this time, I'm going to erase this middle section here. If you look closely at FGY, FGY is adjacent side this time. So that's what we're dealing with cosine. So cosine of theta, remember, is adjacent side, which would be FGY over FG. So what I'm going to end up doing is cross multiplying those two sides to get FGY. So this is going to be, again, 24.5 times cosine of 25.0 degrees. Okay, so I'm going to punch this into a calculator. Again, I'll hit my cosine button first, 25, close my parentheses, multiply by 24.5, and you end up with 22.2 newtons. Okay, so we have FGX and FGY, and we need those when we kind of continue moving forward. Sorry, I'm kind of moving all over the paper here. I'm going to do letter D right here. Says write a net force equation in the y direction, find the normal force. Okay, so net force in the y direction. Look back at my free body diagram. I have two forces in the y direction. I've got a normal force plus my force of gravity in the y direction, which is a downward force, right? One's up, one's down. When those two add together, we get 0. How do we know that? Because it's not accelerating up or down, right? So Fn is actually equal to Fgy, and I already know that number, so I look over here and it's 22.2 newtons. That is what my normal force should be, okay? Now in the x direction, it says write a net force in the x direction and find the force of friction. So if I look in the x direction, so net force in the x direction, I've got two forces. Actually, I've got three forces, right? I've got an applied force, which is to the right. I have a force of friction, which is to the left. And then we also have a force of gravity in the x direction, right? Because that's tilting back downward, that force of gravity. So that's also to the left. But when I sum them all together, I should get 0 because it says it's moving at a constant speed, right? Well, I know the applied force and I know FGX, so I'm just going to solve for the force of friction, right? So I'm going to plug in my numbers and I want to get friction kind of by itself. So here's what I'll do. I'll go ahead and plug in my numbers. It says we have 25 newtons as my applied force, plus the force of friction, minus force of gravity. Remember, it's in a negative direction, 10.4. And that all added together has to give me 0. So when I rearrange this equation, I'm going to move 25 over, and I'm going to move 10.4 over. So 10.4 actually becomes positive, and 25 becomes negative, right? So 10.4 minus 25 when I move them both over. And that's going to give me the correct sign of negative 14.6 newtons is my force of friction, okay? Now, the next thing it's asking me to do is to find the coefficient of friction. Remember the Fun equation? Fun equation is force of friction is equal to mu times Fn. Now, even though the force of friction is negative, we're not going to get a negative value for our mu. So we're going to use kind of the absolute value of our force of friction in this problem. And we're going to get mu by itself. So we rearrange, we divide both sides by Fn, divide both sides by Fn. That way we get the mu by itself. So mu is going to be equal to this 14.6. Remember, I dropped the negative sign, divided by our normal force, which we found over here, 22.2. When I punch this into a calculator, you get, we're going to go 3 sig figs, 0.658 is our coefficient of kinetic friction. Okay, sorry, we're kind of all over the place here. I wanted to make sure all of it was in front of you. We're going to clear and we're going to move on to some more problems. All right, here is our next problem. This time we're going to have a box that slides down the incline. It says a box slides down an incline ramp at 40 degrees above the horizontal. Okay, and then the mass of the box is 12.5 kilograms, coefficient of friction 0.41. The length of the ramp is 0.85 meters. First thing we're going to do is draw a free body diagram. Okay, so I'm going to do that out to the side here. Free body diagram. You've got a force of gravity straight down, right? This time the angle or the ramp is kind of down to the right. So we're going to have to tilt. Our normal force goes this way. What other forces do we have going on? Well, it's friction, right? So up the ramp, opposing the motion, that's our force of friction. Do we have any forces along the down the ramp? We don't directly. We do not have an applied force down. The question becomes, how in the world is this box sliding down the ramp? Well, it goes back to our components. Our force of gravity, remember, has two parts to it. It has this trig triangle. There's an x component, which is down the ramp, and then in a downward direction is this FGY. Now, if you want to draw those on the free body diagram, that would be fine if you wanted to draw that. This angle right here, theta, is actually going to be equal to this angle up here. Okay, there's a property in math that says your angle up here, this theta, is equal to this theta down here. Okay, you've got two parallel lines with a line intersecting it. These two angles would be equal to each other, which is also going to be equal to this angle right here in our trig triangle. Okay, all right. Next part of the problem is we're going to go ahead and we're going to find the components of our triangle, right? So we've got this straight down FG. I'm going to label the hypotenuse this time over here. You've got a y component and an x component. So this is FGX and this is FGY, and you've got theta, okay? Your 90-degree angles right there. And again, like we did on the last problem, if you need to go back and look, since x is the opposite, we're using sine. So to get FGX, you're going to take FG times sine of theta, which in this case was 40.0. And in order to do that, it looks like here, there's a little note that says, well, it doesn't say this, but we probably should find FG out to the side. So I'm going to do that. FG is equal to mg. So if I take the mass, which we said was 12.5, and we multiply it by 9.80, this is going to give us FG. So we can use it in our equation, 12.5 times 9.80. You're going to get 100, and we're going to round up to 123 newtons. So then when I plug this in, I can call it 123 sine of 40. And when you punch that into a calculator, we're going to go sine of 40 times 123. You get 79.1 newtons. That is your x component. Our y component is going to be Fg cosine of theta because it's the adjacent side. So you're going to get 123 cosine of 40. Use your calculator again, hit cosine of 40, multiply by 123, and this time you get 94.2 newtons. So that is our y component, and then our x component is 79.1, okay? Then it says use a net force equation in the y direction to find Fn. So I'm on part C right here. To find Fn, my net force in the y direction, I have an upward normal force and I have a downward FGY. Together, those combined, there is no acceleration along the y-axis. Remember that y-axis is now along normal force and FGY. So therefore, these two are equal to each other. And since I already found the FGY to be 94.2, that must be what our normal force is. Okay, letter D, find the force of friction. How are we going to find the force of friction? Well, remember the fun equation. If we know the coefficient of friction, which we do is 0.41, we can multiply it by that 94.2 normal force, and that's going to give us a force of friction. So we're going to take this 94.2 times 0.41, and you're going to get 38.6 newtons is our force of friction. Now, what can we do with that? We can actually find the acceleration of the box down the ramp. How do we do that? If we know that in the x direction, which is down the ramp, the only force acting is our force of friction. Sorry, that isn't the only force acting, right? We actually have two forces. What's causing it to go down the ramp? Look back at our picture. We've got FGX that goes that way, and then we've got our force of friction that's opposing it. Those two added together is equal to ma. Remember Newton's second law? Net force equals mass times acceleration. We already know the two forces, and we know the mass, so all we have to do is find acceleration. So I'm going to plug in FGX, we found up here is 79.1, minus the force of friction, remember, is opposing, 38.6, is equal to the mass of the box, which we said was 12.5, and that's all going to be times acceleration. So then all I have to do is find 79.1 minus 38.6, that's the left side, gives me 40.5, and then we're going to divide both sides by this 12.5, and that gives me my acceleration. So divided by 12.5, and you get acceleration to be 3.24 meters per second squared, okay? Now, last part of the problem, what will the speed of the box be at the bottom of the ramp? Okay, I'm going to do a quick erase of kind of my midsection, letter C and D here, just so I have a little bit more space, kind of see where we're going, is we have to do a little kinematics, okay? So for letter F, let's think about what we know. We assume the box starts at 0 meters per second. We know it's accelerating down the ramp at 3.24 meters per second squared. Do we know time? We don't. Do we know V final? No, we do not. We know one more piece of information. We know delta X. The length of the ramp, or the displacement as it moves to the right, is going to be 0.85 meters. So that's how far the box is going to move. So we need an equation that doesn't have time in it, but does have VF V0, and A. And here's the equation going back to what we know from kinematics. V final squared is equal to V initial squared plus 2A delta X. Since the initial velocity is 0, this term goes away. To get VF, we're going to do square root of 2 times A times delta X, and we know those values. So we're going to do square root of 2 times 3.24 times 0.85 meters. And we have to take the square root of that, remember? So 3.24 times 0.85 times 2. And then I hit the square root button or to the 0.5 power. And you end up with 2.35 meters per second. That's how fast it's moving at the bottom of the ramp, okay? So we're going to hold on to those numbers. I'm going to write these numbers down. Our acceleration was 3.24 meters per second squared, and our final velocity is 2.35 meters per second. The reason why I'm going to write those down is we're going to redo this problem. What would happen? How would this look different if there was no friction? Let's just assume that it's a frictionless surface. So that's actually our last practice problem here, is what if this box was moving down a frictionless ramp? How would this change things? Okay. That's kind of what we're looking at here. Let's see if I can get my, there we go, ramp to go down. We're going to do this down a frictionless ramp, okay? And the first thing is, what would be different? Well, there would be no friction. So our free body diagram, I'm going to draw this first. Our free body diagram, we would still have our force of gravity straight down. We would still have our normal force at 90 degrees to the ramp. I'm going to draw a little dotted line. There's my ramp. But this time we don't have a force of friction opposing it. So the only thing to think about here is our force of gravity still has those X and Y components. We've got FGX and FGY related to that angle right there. So those are the only forces going on. So in the X direction, this is part B here. In the X direction, we're going to write a net force equation. There is only one force. FGX is equal to MA. We do not have that force of friction this time. Well, from the problem we did before, I wish I would have written that down. FGX was, remember, FG sine of theta, right? So I can do a quick calculation here. FGX is equal to the mass, which we said was, what was the mass of our box here? Actually, let me look. I think I probably have these numbers here in front of me. That'll make things easier if I can just look on my piece of paper here. So we actually are, FGX was, remember, 79.1. So I'm going to plug that in there. 79.1 is equal to the mass of our box was 12.5 and our acceleration. So the difference here is, instead of subtracting 79.1 minus the friction, we just have a net force of 79.1. We're going to divide it by 12.5, and that changes our acceleration significantly. Now we have an acceleration of 6.33 meters per second squared. Wow, that almost doubles our acceleration, right? Oh, actually, I went ahead and did that. That was B and C, it looks like, is net force. We did that, find the acceleration of the box. And then the last part of the problem, let's now find the final speed of the box at the bottom of the ramp. Well, again, our distance or displacement is 0.85 meters. Our initial velocity is 0 meters per second. Our acceleration this time is 6.33 meters per second squared. We're going to find V final. Same equation, VF squared is equal to V initial squared plus 2A delta X. This term goes away. VF is equal to the square root of 2 times acceleration, which is 6.33. And our displacement still is 0.85. So let's recalculate this number, punch it into a calculator. 6.33 times 0.85 times 2. And then we're going to hit to the 0.5 power or square root. And you end up this time with 3.28 meters per second at the bottom of the ramp. So do you see how friction, whether it's present or not, definitely will affect the acceleration and will affect the final velocity? All right, that's kind of tying a little bit of kinematics back in. Make sure you catch main point here. The tilt of that ramp is equal to the tilt of the axis, so that we can use for that for trig to find our X and Y components of our force of gravity.